Newton's first law bears repeating all the time. I said it was central to our physics. Lots and lots of words. Every body perseveres in its state of rest or of uniform motion in a right line unless compelled to change that motion by forces impressed thereon. The second pair of lines there, unless compelled to change that motion by forces. That is our definition of force that we use in our physics. That's not my interest today. My interest is in the first two lines. Every body perseveres in its state of rest or uniform motion in a right line. Even today, in this physics class, we have a simpler way of saying that, more compact, maybe even a clearer way of saying that it's the natural tendency of objects to move with constant velocity. It's more modern. It uses the term velocity, a quantity that describes motion in the context of a magnitude and a direction, a vector quantity. So by creating these definitions, I can use fewer words to express the idea. But when I express the idea this way, I'm using words in a qualitative fashion, and today my main goal is to quantify this idea. But before I do that, I want to let you know that just as we do in all of the English language, when we use our language to describe a subtle or complicated thing, eventually someone is going to come up with a word that means that thing. And we have a word that means every body perseveres in its state of rest or of uniform motion in a right line. There is a word that means that: inertia. Inertia is the name, or if you like, the word that we give to the natural tendency of all objects to move with constant velocity. Now it's good news for me. Standing up here, I no longer have to say all of those words over and over again. When I say the word inertia, that's what I mean. That natural tendency that all objects in the universe are imbued with. I have inertia. A tennis ball has inertia. An atom has inertia. A star, a galaxy, and perhaps even the universe itself has a natural tendency to constant velocity. That is the inertia. Inertia is a property. I have inertia, I just claimed it, but why? Well, the answer today is that we're not 100% clear on why inertia exists in our universe. Remember that my physics is a description of the universe. It's not about the truth or the facts of anything. It's about how I describe the nature of things. That I have inertia, that I have a natural tendency to move with constant velocity, is a fact. Why? Well, we're not really sure. And modern physicists today are working to figure out what is the mechanism. Is there some fine detail about the universe that we haven't discovered yet that is the reason why everything behaves this way? There's a mystery. Inertia is a property of matter. Not every object has the same inertia. I claim that I have a lot of inertia. Well, what does that mean? Well, in comparison, I have more inertia than a tennis ball does, let's say. The way that you would know that I have a lot of inertia is that I have a large resistance to acceleration. If you were to jump out of your seat and try to push me around, which I don't recommend, you would find it is difficult to change my motion because I have a large inertia, while it is very easy to change the motion of a tennis ball. Where it is trivial to change the motion of an atom, it is ponderously difficult to change the motion of the sun. Everything has inertia to varying degrees because everything has, to varying degrees, a different resistance to changes in motion. When I say change in motion, I'm talking about acceleration because that's how we as a physics class have decided to describe it. Acceleration is the quantity in our physics that describes the change in motion. So you could say, you could take everything that I've just gone through and translate it into my inertia means my resistance to acceleration. It doesn't mean that I won't accelerate. It just means that it's difficult to make me accelerate because I have a natural tendency to zero acceleration. I don't want to change my motion. That is inertia, a qualitative description. No one will be surprised that I want to take that qualitative description and turn it into a quantity. But to do that, I need a way of measuring inertia. It might come as a bit of a surprise to you that you already know exactly what I'm talking about. The measurement of inertia is mass. You've already been asked by biology and chemistry teachers in a laboratory to use either an electric or a pan balance to measure the mass of objects. The trouble is, you were likely told that mass is the amount of matter. And that's unfortunate because it's untrue. Shally, why did they lie to me? Well, because they didn't want to get into all this about the natural tendency of objects to move with constant velocity. When you're talking about biological mass in an ecosystem, that doesn't seem to be a relevant thing to be talking about. The fact of all of our science, biology, chemistry included, is that when I'm measuring the mass of a thing, I'm measuring how much inertia it has. When I put an object on a balance, I don't like to think of electric balances because I'm old school. When I put a thing on a pan balance to mass it, I put it on the pan and it goes clunk. And I think to myself, I understand why it just went clunk. The force of gravity on it, its weight, and its weight pulls it down. And I put some other mass on the other side to balance it out, to create an equilibrium that by comparison will tell me a number of grams or kilograms that mass is. When you measure mass, you are not measuring weight. When you measure mass, you are not measuring the force of gravity. When you measure the mass of a thing, you are measuring its inertia, this property that it has, described by Newton's first law. Mass is not the amount of matter, which is completely contrary to what they might have told you in chemistry class. I don't know exactly the words they use at this school, but they may have said, oh, look at these atomic weights on the periodic table. When you talk about the atomic weights of atoms as they're arranged in chemistry, you're not talking about the gravitational force on the atom. What you're talking about is the atom's inertia. Why didn't they just say that? Well, because they didn't want to have this discussion about what mass is in fact the measure of. And it turns out to be not coincidental, but incidental. That when you determine the amount of inertia that a thing has by measuring its mass, you have also accidentally figured out the number of the different atoms that make up that object, because atoms are composed of protons, neutrons, and electrons, and all of the subatomic particles have inertia. They have mass. And then the total mass of an atom, it would seem like, by the way, that the total mass of an atom is the sum total of all the particles. That turns out not to be true. There's a mystery of the universe that hides in that, a beautiful mystery. But nearly. The mass of an atom is nearly the sum of its parts in terms of its mass. So then chemistry folks who are interested in the number of atoms that go into a reaction and the number of atoms that come out again, they have a tendency to talk about mass as if it's the amount of matter. It is not. Mass in biology, chemistry, and physics is always the measure of inertia. This one is a killer. This one is the bane of the existence of every physics teacher everywhere on the earth. Mass and weight are not the same thing. And the reason why that's a problem for students is that I have already made the claim that I am massive. I have a large mass because I have a large inertia. But I'm also heavy, and a tennis ball has a small inertia, a small mass, and is light. It is very easy in our mind to connect these two things, that mass and weight are the same. They are not, and I wouldn't be making a big deal out of it if it didn't really matter. It matters a lot. Mass is the measure of an object's inertia, and gravity, weight, is a force. They are not the same thing. Now, if you're interested in being a physicist, that really matters. But if you're a student of physics and you're interested in getting right answers, that also matters a whole lot. So, inertia is the word that I use. The measurement of inertia is mass, in the same way that the measurement of space is displacement. The measurement of motion is velocity. Mass, the SI unit, is kilograms. In chemistry, of course, you used a lot of grams because a kilogram of sodium chloride is a lot of sodium chloride. So in mass, you use a lot of grams, but our SI unit for mass, our central unit that we use for our physics, is actually the kilogram. because unlike the chemists, we're going to be interested in the motions of airplanes and automobiles, which have much larger masses. The unit of mass is the kilogram. Now, not our first equation of physics, but here's an equation for you. The weight of a thing is equal to its mass multiplied by little g. Hang on, the same little g we were talking about before, the acceleration due to gravity, where a thing that falls under the influence of its own weight adds 9.8 meters per second every second. The little g that is 9.8 meters per second squared, yeah, that one. To calculate the weight of a thing, you take its mass in kilograms and multiply by 9.8 meters per second squared. And that is the weight of a thing in newtons. Well, Shadi, okay, fine. So they're the same thing. If you take the mass and you just multiply by a constant number, then the weight is just different by a constant. What is the big deal? The big deal is that the acceleration caused by gravity is only 9.8 meters per second squared here on the surface of the Earth. Everywhere else in the universe, it's different. Here on Earth, I have a certain mass. Let's not worry about what it is in kilograms, but I have a certain mass. If I go to the moon, I have the same mass. If I go to Mars, I have the same mass. If I go to Jupiter, I have the same mass. My mass is the same everywhere I go in the universe because the mass is an inherent property that I have. The mass is a measure of my inertia. But here on the surface of the Earth, I have a weight, a certain number of newtons of gravitational force that acts on me as I stand here before you. If I go to the moon, I weigh 1/6 as much. If I go to Mars, I weigh 1/3 as much. If I go to Jupiter, I weigh 12 times what I weigh. Mass and weight are not the same quantity. It's going to be a little struggle to keep that clear. I'm going to continue to emphasize it. Mass and weight not the same. For example, if I have a 5 kilogram mass and I want to calculate its weight, I'll simply take 5 kilograms and multiply by 9.8. Easy peasy. Everybody gets it. 5 times 9.8 works out to be 49 newtons, or if you're willing to do it approximately and use 10, it works out to 50 newtons. An object that has a mass of 5 kilograms has a gravitational force acting on it of 49 newtons. If I'm given, as a student of physics, a weight, let's say I'm told in a problem statement that a thing weighs 100 newtons, then I can calculate how much mass that is by taking the weight and stirring this equation around so that the mass is the weight divided by g. I'll simply take 100 newtons and divide by 10 meters per second squared, a little approximation, and that's 10 kilograms. That's exactly what the pan balance is doing. The pan balance only works on the surface of the Earth because the pan balance is using 9.8 meters per second squared to scale the mass of an object. If I take a pan balance and I put it on a rocket and I fly to the moon with it and I try to determine the mass of objects, I'll get wrong answers because the pan balance, whether it's digital or mechanical, is calibrated to the acceleration due to gravity here near the surface of the Earth. Mass, the measure of an object's inertia.